Welcome PCS members and friends to our today's Thursday PCS IBS seminar. It is a great pleasure to have with us today Dr. Minsung Kim from Ulsan National Institute of Science and Technology. And I would like to invite our scientific host, Sergey, to introduce our speaker. Please, Sergey.
Yeah, thanks, Tilen, and also welcome to everyone. It's a great pleasure to have Dr. Minsung Kim with us today. Let me tell you a few words about him, about his career. He did his bachelor and PhD studies at the SNU, Seoul National University, and he finished his PhD in 2014. But he didn't just finish it, he finished it with the Best Doctoral Thesis Award from the College of Natural Sciences. Then he stayed there for less than a month, if I get it right, as a postdoctoral researcher, only to move then to Ames laboratory, where he spent 4 years as a postdoctoral research associate in the United States. Then from there he moved to Rutgers University, where he worked for another 2 years as a postdoctoral associate. And very early this year, in February, he returned to Korea and is now working at the Department of Physics of UNIST, Ulsan National Institute of Science and Technology. Minsung Kim has more than 20 publications in a number of very well-known journals. And his research interests are, it seems to me at least, mainly focusing around such topics as correlations, topology, topological materials, topological insulators, semi-metals, superconductors, and the such, nanomaterials with novel electronic structures, spin-orbit coupling, quantum geometric tensor issues, superconductors in general, spintronics, and one interesting bullet point which I read here, which is basically anything which is conceptually or mathematically new, which I like very much. So I think with that, I should not steal more time from our speaker. Minsung Kim, the floor is yours, please.
Yeah, thank you for the kind introduction, and also thank you for inviting me and giving me the opportunity for presenting my recent research. And today I will, my name is Minsung Kim, as introduced, and today I will talk about orbital-selective Mott phase and non-Fermi liquid state in iron phosphorus trisulfide. Basically, the content of this talk will be can be found in this published paper. So let me start by introducing this material. This basically this is a layered material system, and experimentally there are two important reports. One is the by the way, at ambient condition, this material is known to be Mott insulator, and electronically it is reported to undergo an insulator-to-metal transition under pressure, as reported in these papers experimentally. And also, there are structural phase transition with 3 different types of structures, and also reported in this experimental and also in this theory paper. So basically, we have 2 different types of phase transitions: electronic phase transition and structural phase transition. So it is basically kind of complex theoretical problem to properly understand the structural transition part and electronic transition part, and also the relation between the 2 different types of phase transition. And also, this material is already Mott insulator at ambient conditions, so the proper description of the electron correlation effect is essential. And actually, in passing, I want to make some comment about this closely related compound, which is not a topic of present talk, but maybe possibly interesting in as a future work. So in this material, the sulfur atom is replaced by selenium, and this material also shows similar sequence of structural phase transition and also insulator-metal transition. But one interesting point is that under pressure, experimentally, people reported the appearance of superconductivity, which potentially implies some connectivity to ion-based superconductor. And actually, there are other combination of the, many other materials in this material class by changing this M atom and S atom to this type of atoms. So basically, I think this material system provides an interesting and promising opportunity to study the effect of electron correlation in layered antiferromagnet. Now, this is the outline of the talk. As I mentioned in the previous slide, this material has both structural and electronic phase transitions. But in this talk, I will just focus on electronic phase transition. So I plan to present very brief review of the structural phase transition under pressure, and then I will move on to the electronic phase part. We performed first principles calculations using density functional theory and embedded dynamical mean field theory. And we will study the Mott insulator to metal transition, and especially try to study the character of the metallic phases. But in reality, in real experiments, it is kind of commonly occur where the situation is not very ideal, and there are some inhomogeneity in the pressure conditions. So I will address that issue later as a non-hydrostatic pressure effect. And also one of the main findings in this study is the emergence of two different metallic phases, non-Fermi liquid and Fermi liquid phases. So this non-Fermi liquid phase is actually attributed to the appearance of the so-called orbital-selective Mott phase. And I will explain how they are why they are interesting and how they are different from conventional Fermi liquid phase. And for the origin of this, for the origin of the appearance of two different phases, I will explain in terms of the competition between Hund coupling and the crystal field splitting. And also I will try to clarify the relation between the structure and the electronic phase transitions. And finally, I will make some comment about the temperature dependence of the resistivity in our calculations. So let me start from explaining the atomic structure of the system. So basically, this is a layered structure with van der Waals gaps between this triple layer unit, where at the center of the triple layer unit, we have honeycomb lattice of iron and sandwiched by two triangular lattice of sulfur. And also at the center of the iron Fe hexagons, we have vertical P dimers. The notable feature of this structure is that at ambient condition, actually the stacking of this triple layer unit is kind of tilted. So it's in kind of in a staggered way so the result is that it adopts a monoclinic space group where the monoclinic angle is about 107 degrees, if I remember correctly. So this is the 3 different structural phases under pressure for their representative pressure value, 0, 10, and 18 gigapascal for HP0, 1, and 2 phases. Basically, this sequence of structural phase transition is confirmed, already reported by experimentalists in this paper. And what they observe is that the first phase transition from HP0 to HP1, there occurs a layer sliding between these neighboring triple layer units. And for the second phase transition, they report, which occurs around 14 gigapascal, they report the interlayer collapse, where this van der Waals gap is now collapsed to form a chemical bonding between the can be easily by name for in this not aligned but stacked in a staggered way. So we call this staggered p-dimer phase. And in this case, p-dimers are almost aligned, and we'll call this aligned p-dimer phase. And finally, in this phase, actually these p atoms make chains instead of separate dimers. So we will call this aligned p chains. Actually, one thing I should mention, one thing I need to mention is that this monoclinic ambient condition phase has already some implication about this series of structural phase transition, because if we compare with the other material, this chromium germanium tritelluride, actually this material is famous for the realization of two-dimensional ferromagnetism very recently. And in this material, the structure of this triple layer unit is actually the same with this FePS3, but the difference is that the stacking is something like ABC, ABC, and actually it adopts rhombohedral structure at ambient condition. So experimentally, they report isostructural insulator-to-metal transition under pressure without this kind of layer sliding or interlayer collapse transition. So basically, the way how these triple layer unit stacks at ambient condition is very important for the existence of this type of structural phase transition or not. Actually, I'm giving a contributed talk in this upcoming APS March meeting next week, and if you are interested, please you can come and check my recorded video, because I'm not actually going to Chicago, but just attending virtually. So let me move on to the result of my calculations. So this is the calculation of enthalpy versus pressure using density functional theory method, where I put the details of the calculation in this blue box. And what we can see is, by the way, this is a relative enthalpy with respect to this HP0 phase. So actually HP0 is all the way 0. And what you can see is that initially both HP1 and HP2 phases are less stable, but under beyond some critical pressure around 6 gigapascal, we find that the HP1 phase is most stable phase, and maybe beyond about 15 gigapascal, we find that HP2 phase is the most stable phase. So actually, this is reproduces the experimental structure phase transition very well, and also actually this very similar result was already reported in a theoretical paper here. So in terms of the change of the volume and the lattice constants, we can actually confirm that our ab initio theory described the structural phases very well. For example, this is pressure versus volume result, and what we can see is there is abrupt change in the second structural phase transition from HP1 to HP2 phase. So basically, this is attributed to the interlayer collapse, where the formation of P chains reduces the volume significantly. And also, in terms of lattice constants, you can see that only C lattice parameter has a big change from HP1 phase to HP2 phase. So basically, this is also consistent with the experimental observation. Now, let me move on to the electronic phase transition part. So basically, we have 3 different phases, and for HP0 phase, we already know it is supposed to be a Mott insulator, and for HP2 phase, we know there is no ambiguity. We know HP2 phase is metallic, but there are some tricky thing about this intermediate phase HP1, because in some experimental paper, they report this HP1 phase is metallic, but in another experimental paper, they report this phase is actually gapped. So, but the situation is that these 2 papers are from the same group, so there is this seemingly this is contradiction, but actually it's not, because the experiments were conducted in a different condition. That is, this former experiment was conducted under non-hydrostatic pressure, because in this experiment, they used pressure transmitting, powder pressure transmitting medium, which can make some inhomogeneity in the pressure conditions. So but in the later experiment, they say the experiment was performed under effectively hydrostatic pressure. So actually, in my experience, this kind of inhomogeneity in pressure condition is kind of a common thing in the diamond ambient pressure experiment. So actually, I think in my experience, the best way is just contact the one of the authors who actually performed the experiments and clear out what would be the exact pressure configuration in their experiments.
Minsung, can I ask something?
Yeah.
So this hydrostatic pressure, this means isotropic.
Yeah.
Is this? And the other one has some
anisotropy. Yeah, I will elaborate in the next slide. Yeah.
Okay, thank you.
So, yeah. So
I have also a question, Minsung. So are there also such structural phase transitions in these materials upon varying temperature at, so to say, normal pressure, or is the only way to reach these phases so far to apply pressure?
Actually, if I remember correctly, there is no structure phase transition reported at low temperature. As far as I know, no. But these experiments are actually conducted in room temperature, and as far as I know, maybe there is no low temperature structure.
Thank you.
We also have a question from Alexei.
Yeah, thanks. It's basically, in some sense, a continuation. I'm curious, can you also induce this transition or some sort of transition by changing the pressure in time, say periodically applying, well, increasing and decreasing the pressure?
Oh, you mean some kind of vibration or something?
Yeah, more or less. So yeah, I mean, I'm thinking of a situation where you would change the pressure periodically in time, for example.
Actually, I'm not quite sure. But once I think regarding your question, I think I need to mention something about this phase transition. So basically, I mean, in this layer sliding transition, the neighboring triangular surface lattices favors to make close packed configuration. So this is layer sliding means this neighboring layers adopt another close packed configuration. So basically, this is kind of discrete translation, and this phase transition is actually first order phase transition. So basically, this value of critical pressure is just when, I mean, near the 4 gigapascal, we have 50% of HB0 phase and 50% of HB1 phase. So if you want to change the pressure periodically in time, I think it's not kind of really changing all the structure to HB1 and HB0. Maybe it's just some changing some relative portion of the structures in the example. Yeah.
Yes, but then actually I have one subsequent question. I think Thielen asked before, this is isotropic. The pressure is applied isotropically, right?
In the later experiment, yes.
But then you mentioned that at least the first transition corresponds, if I understand correctly, to sliding of the two layers.
Mm-hmm.
Wouldn't it then make sense to apply the pressure exactly along along this direction? Because this in principle should facilitate this transition and perhaps make it easier to see experimentally.
So actually, in the later slide, I will discuss the effect of the non-hydrostatic pressure in view of electronic structure. But actually, I don't have the figures in this PPT right now, but as far as I checked, there is no effective difference in terms of structural phase transition, whether you apply hydrostatic or non-hydrostatic pressure.
Okay.
In terms of enthalpy, yeah, calculation, yeah.
Okay, thank you.
I have two questions. One, do the electronic transitions happen exactly at the same pressure as the structural transition? And two, how does the conductance behave as function of pressure? Can you describe it as a gap closing as function of the pressure?
Yeah, actually, for the first question, I think it's not necessarily the two types of phase transition are not necessarily occurring at the same pressure, because mode transition is basically not basically it's kind of quantitative question, right? So I think the sliding itself is not essential to induce the electronic phase transition, the mode transition in principle. So, but in this system, it's just that the instability of the structural phase transition is just near the electronic mode transition, which I did not really carefully checked or any fully detailed calculation result. So, but in principle, they are kind of independent, right? So, can you repeat the second question because I forgot?
Yeah, the question is, as you increase the pressure, presumably the hopping, tunneling energies become larger, the gaps, the bands become, the single electron bands become broader, and you could think that the Mott gap closes. Is that a reasonable picture here?
Actually, I think it's basically competition between the kinetic energy and interaction energy, right? So if you are asking whether the is your question asking the difference compared with other simple mode Hubbard transition, or are you asking? I don't expect the crucial difference from conventional mode transition, but as I will describe later, in this system, there is some difference in terms of which orbital are participating in the mode transition. And actually, it turns out that only part of the d orbital participate in the mode transition, while the remaining stage, while other d orbitals remain gapped. So basically, I think the answer for the second question will be clarified as this talk going on.
Will you show us data of the conductance as function of pressure?
Actually, I think basically this paper reports the temperature dependence of the resistivity for a number of different pressures. So basically, we have resistivity or conductivity data. Yeah.
Can the temperature dependence at a fixed pressure be described by a gap, by an Arrhenius like an exponential of a gap over temperature?
Actually, if I remember correctly, there was some argument about temperature dependence of resistivity and size of the gap. So, but as far as I remember, I don't remember anything special compared to the usual RNA type argument, right? So, yeah, they just a argument regarding how the temperature dependence of resistivity behave at the high temperature, if we whether it's increasing with the temperature or decreasing with the temperature, to study the metal insulator to identify the metal or insulator phases in this system.
Okay, thank you.
There's a question in the chat from Hyung-Jun Lee. Hyung-Jun, do you want to ask it or shall I read it? If you don't react, I will just read it.
We don't see you, Minsung.
He doesn't seem to react, so let me just read it. He wrote, I have a question. How do you apply the pressure on your systems / calculations, and how to estimate your pressure values?
Actually, what I do is I actually in this numerical density DFT calculation package, we can basically calculate the stress on the unit cell for each boundary of the unit cell, and we can actually by applying pressure, we just mean that we have some condition with whether you, for example, add a factor to set the pressure, not to set the stress, not the exactly 0 point, but have some finite value. And that's how I just calculate the electronic structure for different pressure in practical calculations. So,
okay, let's hope that answers Hyung-Jun Lee's question. Yeah, he thinks. Okay, let's go ahead.
So to study the electronic phase transition in this system, we performed first principle calculation using embedded dynamical mean field theory, where I put the details of calculation in this box. And basically this calculation is paramagnetic for paramagnetic state at 300 Kelvin. And this is the K result of the spectral function and projected density of state for HP0 phase at 0 gigapascal. In this system, basically, the relevant crystal field is octahedral, so there is T2G-EG splitting, but due to the layered structure, we have also some amount of trigonal field, so this T2G state further split into A1G and EG prime states. So as you can see, in this HP0 phase, all the T2G and EG states have a gap, and we can see the incoherent Hubbard band around the Fermi energy as expected from the Mott insulator nature. For the HB1 phase at 10 gigapascal, as I mentioned in the previous slide, it's important to correctly describe the the dependence of the metallicity on the non-hydrostatic pressure condition. So let me first introduce some notation here. So experimentally, the situation is that we have a larger pressure component in out of plane direction than in plane. So just put a factor PL here, where it measures how large is the G component of the pressure, where the overall pressure is always kept at 10 gigapascal. So simply speaking, if this PL is 1, it means hydrostatic pressure. And if this PL is larger than 1, it means non-hydrostatic pressure with larger pressure component in out of plane direction. So as I mentioned earlier, the important experimental feature is this phase should be gapped at hydrostatic pressure and should be metallic under non-hydrostatic pressure. So this is the series of calculation with varying PL factor here. So for hydrostatic pressure, we still have a small gap, and there is a very clear tendency where as we increase this PR factor, we have a more metallic density of state at the Fermi energy. Actually, this can be attributed to the hybridization of the, layered features of the structure. Basically, larger PL tends to reduce the bonding distance between Fe and sulfur S atoms. So, and this in turn increases the hybridization, as you can see from this calculation of impurity hybridization function delta in one of the T2G states. So basically, if this hybridization increase, it will favor the metallicity of this T2G state. So basically, this type of tendency, this tendency is closely related to the layered atomic structure. And one thing we can find interesting is that in this Mott transition, you can see that only T2G states become itinerant, while this EG gap is still persists beyond this metal insulator transition. So historically, this state is called orbital-selective Mott phase. In our case, T2G is metallic, but EG remains gapped. So basically, in this phase, it is expected that we should find some incoherent metallic state near the Fermi energy. Actually, the reason is that the localized electrons, in our case EG, act as a scattering center for the itinerant electrons, in our case T2G electrons. So, but in contrast, this H2 phase has also metallic density of state, but has very clear quasi-particle peaks near the Fermi energy. So this is basically imply that the two metallic states in HP1 and HP2 are qualitatively different. So to explain the qualitative difference in more detail, we performed the calculation of scattering rate. Actually, scattering rate is just proportional to the imaginary part of the self-energy on imaginary axis, close to omega 0. So basically, in these figures, it corresponds to the y-intercept of the graphs. So in HB1 phase, at high temperature, we have large scattering rate. And in HB2 phase, we have very small scattering rate. And for the lower temperature calculation at 100 Kelvin, in HP2 phase, the scattering rate actually become negligible, and the omega dependence is almost linear near the omega equals 0 point, just as expected from conventional Fermi liquid theory. But in this HP2 phase, I mean HP1 phase, we still have some sizable size of the scattering rate, which implies some fundamental difference from Fermi liquid state. And also, one thing I should mention is that the behavior near the omega equals 0 point is very different. And actually, this behavior is reported to be logarithmic, as reported in one of theoretical model study in the literature. So what is the origin of the big difference in the two metallic states? I would say the difference comes from the relative strength of the Hund coupling and crystal field splitting. So in this system, basically we have Fe2 plus ions, which means we have 6 electrons in 3D cell. So suppose we have a very large crystal field splitting, and the electron will just favor to occupy the lower T2G state, which is just energetically lower. So that situation corresponds to this HP state. So in this HP2 state, the crystal field splitting is dominant, and the electrons will try to occupy mostly the T2G state, which in turn will result in low spin configuration. But the opposite case, the large Hund coupling limit is just this HP1 page where we have dominant Hund coupling effect. And so simply because Hund coupling try to align the spins of the electrons, we will have rather similar occupation in T2G and EG state with high spin configuration. Actually, it can be quantitatively checked by calculating the, for example, average occupation per orbital and also probability of each spin state. So, for example, in this HP1 phase, we have rather similar occupation in T2G and EG state, but in this HP2 state, we have somewhat larger T2G occupation than EG occupation. And also in this spin statistics, we can say that high spin configurations are dominant in HP1 phase, while we have low spin configuration dominant in the HP2 phase. Actually, we can do one trivial check for the effect of Hund coupling in this system. That is just artificially setting this Hund coupling parameter 0. Then we will expect that HP1 phase will just become very similar to HP2 phase, and this is the result. And you can see that this speed projected density of state already suggests that we have most d electrons in T2G state, and EG states are mostly empty, which is very similar to the situation in HP2 phase. Now let's discuss some naive features. For example, one may expect, the situation in this orbital-selective Mott transition is something like we have two decoupled band manifold, and we have two different critical strengths of Coulomb interaction for different orbitals. And so naturally, we will expect some more decoupling effect between orbitals in this OSMP phase rather than other phases. So it can be directly checked by computing the orbital fluctuation by this formula. And this is just represent the correlation in the occupation of state A and B, as you can see. And if we calculate this number for HP1 and HP2 phase, we can readily check that the orbital fluctuation is actually relatively suppressed in HP1 phase compared with HP2 phase. Another point that I mentioned regarding the orbital-selective Mott phase is the qualitative understanding how and why the OSMP occurs in this system. So the situation is we have 6 electrons in 5 3D orbitals. So suppose we turn off the crystal field, then we will have 6/5 electrons for each orbital evenly, right? Then suppose we gradually turn on the crystal field, then the occupation in EG state will decrease simply because EG is now in higher energy. Then at some point, EG state becomes half filled, and in this case, we can have orbital-selective Mott transition in our FePS3 material, basically because these due to the large intercoupling, we have suppressed orbital fluctuation. So this very similar argument is already proposed in a 3-band model study with 4 electrons in one of the paper in the literature. Now let me discuss some comparison with other systems that was discussed in the context of OSMP in the literature. So first one is a heavy fermion system. Actually, some people argue that Kondo breakdown can be regarded as a special case of orbital-selective Mott transition. But one important difference is that in this F electron system, we have a very large difference in the bandwidth of F electrons and other orbitals. But in contrast, in our case in multi-orbital transition metal system, the relative bands have all similar bandwidths, and actually the OSMT comes from the interplay of Hund coupling, the crystal field, and the electron fielding, as I described in the previous slides. So I think more analogous example is ion-based superconductors. The only difference is that the crystal field tetragonal in Fe-based superconductors as opposed to our octahedral in our system. But as far as I know, there are some models studied proposing some orbital selective physics in the ion-based superconductors. But as far as I know, all the first principle calculation in ion-based superconductors actually result in Fermi liquid phase rather than any orbital selective Mott phase. So maybe it would be interesting future topic, how we can clarify the relation in terms of the Hund coupling or any difference in crystal field configuration between this FePS type compound and ion-based superconductor. Now I will just briefly try to understand the relation between the structural and electronic phase transition. So in this figure, what I did is just did calculation for some fictitious metastable state. So for example, this actually this thicker borderline means these states are stable state at their respective pressure values. So we should have HP0 structure at 0 gigapascal and HP1 structure at 10 gigapascal. But what if we use HP0 structure at 10 gigapascal? This by comparing these two results, we can simply estimate the effect of layer sliding on the electronic phase, right? So by comparing these two figures, what I find is just in this case, we still have some small gap near the Fermi energy. So this, simply speaking, this means that layer sliding helps the metallization of the T2G state. And now I did a calculation for HP1 phase at 18 gigapascal, which is also fictitious metastable structure. And if we compare this one with this stable structure, HP2 at 18 gigapascal, we can see that these two density of state suggest very similar feature. So where the most of the T electrons would just occupy the T2G state, just as in the case of HP2 phase. So basically, the interlayer collapse is not very essential to break this OSMP and to realize the Fermi liquid phase in this system. Actually, this is plausible because in principle, if we increase the strength of the crystal field, eventually we will have a large crystal field limit case as in HP2 phase. And also, this one is just to estimate the effect of interlayer collapse in the other limits. So I just performed calculation for HP2 at 10 gigapascal. And as you can see, this fictitious phase still have a Fermi liquid feature and do not have orbital-selective Mott phase. So this means that interlayer collapse is kind of useful to increase the strength of the crystal field, because at the same pressure, once we have interlayer collapse, the effect of a crystal field is already very large. So finally, I will just make some comments about my resistivity calculation. So in this, for this resistivity values, I just performed optical conductivity calculation, and using this optical conductivity, I just obtained the DC resistivity. And actually, as you can expect it from the non-Fermi liquid nature, this is just relatively high resistivity value. And so this material is basically bad metal. Maybe you can remember that good metals such as copper will have 10 to the -6 order resistivity value. So and also the lower panel just correspond to the calculation of self-energy on imaginary axis and for the scattering rates, and basically should have the same trend upon changing the temperature. So one thing I should mention is that experimentally there is about 2 orders of magnitude difference in the resistivity of HP1 and HP2 phases at high T regime. So basically in our OSMP scenario assumes some intrinsic change of the character of the metallic state. So this is kind of a plausible scenario because this naturally explains the large resistivity difference in HP1 and HP2 phase. Actually, when we submitted these results to the journal, one of the referees asked, do you have any clear experimental feature which can be explained only by your OSMP scenario, but cannot be explained otherwise. But I think such kind of thing is not, I mean, I cannot give any such clear evidence, but this this big resistivity difference by almost 2 orders of magnitude is already implies some intrinsic change of the character of metallic states in HP1 and HP2. So this is the conclusion. In this talk, we studied electronic phase transition and also some structural phase transition. We had 3 different structural phases, and the first transition involved layer sliding, and the latter transition involved interlayer collapse. And in the electronic phase transition part, we had 2 different types of metallic state. One is non-Fermi liquid state, and the other is Fermi liquid state. And there are lots of contrasting features in terms of scattering rates and quantum coupling and crystal field, and also for the orbital fluctuation and spin configuration, and also for the resistivity. And this FePS3 material is kind of interesting system because it shows 3 contrasting phases: Mott insulator, non-Fermi liquid, and Fermi liquid in an accessible pressure range. Thank you for your attention.
Thank you, Minsung, for this interesting talk. Let us thank our speaker. And we have time for questions.
Let me just start shooting with one question. So again, coming back to this also question, I think which was raised by Amnon. He was asking whether this increasing of pressure can be just viewed as pulling the making, so to say, the lattice constant smaller, and therefore increasing the tunneling rates, and making the kinetic energy stronger, right?
Yeah.
And is that also how you would view these is that how you view the mechanism of these phase transitions, of these structural phase transitions, or is it something different?
Actually, for the relation of the electronic and structural phase transition, what I'm thinking is actually, in principle, the electronic mode transition can occur without a structural phase transition, and the structural phase transition in this system is just kind of ad hoc process, which is just come from the instability due to the monoclinic structure at ambient condition. So in my opinion, they are not very essential affecting each other, but it's kind of just quantitative problem where the structural phase transition occur near the electronic critical point or not.
Near means not exactly at. Is that what you want to say? So there are two different critical points.
Yeah. So basically, what I'm saying is we can find an example where the situation is very similar, but this material just do not have a structural phase transition, and we can very similarly find mode insulated to metal transition in this system. Actually, this one is charge transfer insulator rather than mode insulator. So the situation is a little bit
which
different.
brings me then to the question, so what is then driving these structural phase transitions?
Actually, let me try to explain, give some naive explanation. So suppose we have, because in this system we have van der Waals gaps, right? So I think, suppose we apply very large pressure, and eventually, regardless of the structure, eventually the system would favor the collapsed phase. Removing this van der Waals gap. But in this system, the important point is that it would be better to align these p dimers, because in this collapsed system, this chemical bond, interlayer chemical bond between these p atoms would somehow stabilize the collapsed phase. So in this sense, this intermediate phase, the slided phase, is kind of prerequisite for the this collapsed phase, simply because we need to first align these p dimers before we have this type of interlayer chemical bonding. So basically, what I understand is that for to have this type of collapsed phase, we need to first align the p dimers, and then we can have this type of collapse of van der Waals gaps. So basically, this is kind of naive and qualitative understanding of structural transition in my point of view.
Thank you.
Perhaps let me ask, so you were mentioning in the beginning that one of the systems that you are currently also interested in is by replacing the sulfur with selenium, right?
Yeah, this one, yeah.
So, it seems, since you report here that this work experiment found superconductivity, I would ask, is this ambient temperature, or is it some lower temperature?
Basically, I remember that the transition temperature for the superconductivity is less than 10 Kelvin. So it's not high TC. So
and under
actually
pressure.
Under pressure, yeah. So basically, the authors argue that they suggest some potential connectivity to ion-based superconductor. But for now, I think it's not clear whether this superconductivity is just conventional BCS type or not. So, yeah, still unclear.
Is the structure very different from your case?
If I remember correctly, the ambient condition structure is different, but it also adopts this kind of collapsed phase. Yeah, as far as I remember. Yeah.
And this is then the phase that turns superconducting, or?
I need to check. Yeah, because I do not remember exactly the critical pressure for the appearance of superconductivity in the selenium compound. Yeah.
Okay, thank you. Do we have any further questions from the audience? Seems not. So in this case, let us thank Minsung again. And with this, we conclude our today's